The aims of this video are to describe what statistical power is and why it's important, and to explain what factors influence power, and directly following on from that, what factors go into a sample size calculation. So first of all, let's define what we mean by power. The power of a study, or more specifically of a statistical test, is the ability to detect a difference or an association or an effect when a true difference exists. A key component of statistical power is sample size. All other things being equal, and we'll come on to what those things are a bit later, a larger study will have more power or will be more likely to detect a difference when one actually exists. So a larger study is more powerful. Too many studies lack the information or are too small in terms of sample size to be able to answer the research question that was asked. They lack power. What this means in practice is that they are a waste of time and resources, but can also work in the opposite direction too. For example, recruiting too many subjects or processing too many biological samples than is necessary to answer the research question is also a waste of resources. If the study is a clinical trial, there may also be ethical implications. It's unethical to ask patients to participate in a trial that can answer the research question. Plus, it may draw incorrect conclusions. It's also unethical to recruit too many subjects if the treatment works, because this means that more patients than necessary would have been exposed to the placebo or the less effective treatment, and the beneficial effects of a therapy would be delayed. So power is important, particularly in planning and investigation. So let's first of all define it. Now, despite telling you that we should interpret p-values in a continuous way as a strength of evidence against a null, I will now need to talk about either rejecting or accepting a null hypothesis based on a p-value threshold. And that's just the way we have to simplify things to understand power and do sample size calculations. It does not mean that p-values have to be interpreted in this binary significant, non-significant way. So if we do an experiment or a study, there are 4 possible outcomes. First of all, the null hypothesis is true, but we reject it. We call that a type 1 error. The probability of making a type 1 error is dependent on the p-value cutoff we specify. This is often abbreviated alpha. So if we have a 0.05 cutoff, then 1 in 20 times we'd expect to falsely reject the null hypothesis. And this is captured in the tails of the distribution, the sampling distribution here. The complement is that we correctly fail to reject the null when it's true, and that's equal to 1 minus alpha, or 1 minus the probability of a type 1 error. We may also fail to reject the null when it's actually false. We call this a type 2 error, and the probability of that happening is denoted by the letter beta. So beta is the chance of making a wrong decision. Its complement is to make the right decision when the null is false. That's correctly rejecting the null when it's false. And this is equal to 1 minus the probability of a type 2 error, or 1 minus beta. And this is called the power of a study. And it can be visualized here. So the true difference is represented by the distance that the 2 sampling distributions here are apart. That's denoted by the letter delta. Now this is a distribution under the null, which we use to calculate the p-value. However, in the case of a true difference, we also have to think about the distribution of the point estimate under the alternative hypothesis, i.e. that they're different. But you can see that sometimes when there is a true difference, just due to sampling variation, the observed difference will fall within the fail to reject region of the null distribution, in which case a type 2 error is made, and that's captured here. So the power of the study then is captured by this region here. Typically, we like to have a power of at least 80%. This means that if there is a true difference of a specified size delta, then the chance of detecting it with our study is 80% at a designated significance level. So just looking at this graph, you can hopefully see that power depends on alpha, or our level of significance. So the bigger alpha is, then the more power. The size of the study. A bigger study will make the two sampling distributions narrower due to a smaller standard error. Power also depends on the variation in the sample, or the standard deviation. So if there's less variation, then that means a smaller standard error and a narrower sampling distribution. Or thinking about it another way, if you're looking for a difference between groups and there's a lot of variability or noise in the data in each group, then you will need a bigger sample to detect the signal in amongst all that noise or variability. And lastly, power depends on the size of the difference to be detected. So all else being equal, we will have more power to detect a larger true difference. And this just bullet points those 4 factors that influence power. So you might want to pause the video. So to maximize power, there are 4 things to play with. We can use a larger or less stringent p-value or alpha threshold. We can increase the sample size. We can reduce the variation in our samples. Or we can increase the size of the difference to be detected. But most of these things we cannot manipulate. Alpha is conventionally set at 5%. The standard deviation is determined by the variation in our sample. And the difference to be detected is determined by clinical factors. So the main thing under our control to increase power is to increase the sample size. And that is why we do a sample size calculation. And we perform a sample size calculation when we want to estimate some quantity with a particular precision, i.e. with a particular width of confidence intervals, when we want to demonstrate the equivalence of 2 groups. And most commonly, so that we can have sufficient power to detect a difference between 2 groups or to detect an association. So a sample size calculation is done to answer the following question. What size sample do we require to be able to detect our target difference between 2 groups with pre-specified power and significance level, given the variation that we have in the sample? That's a bit of a mouthful, but you can see 4 conditions upon which a sample size is based. The target difference, the power that we want to have, the significance level we're going to use, and the variation that exists in the sample. So these are the 4 factors that we typically need to specify to do a sample size calculation. So first of all, we need to define the smallest effect that we wish to see, the smallest clinically or scientifically relevant effect. Then we also have to have an estimate of the population standard deviation, and typically we use empirical estimates from other studies or perhaps some pilot data to estimate that standard deviation. Then we have to specify the power, and as said, we typically choose a value between 80 and 95%. Then also what significance level, and that's typically 5% or 1%, or p equals 0.05 or 0.01. The actual equation for a power calculation itself depends on what you're trying to estimate. So there are different equations for different effect estimates. So this is typically the sort of statement you will see when someone reports a result of a power calculation. So we chose to study 313 patients in each group to have 80% power to detect a 33% reduction in the recurrence rate from a baseline rate of 30% with a 2-tailed significance level of 0.05. So there's a lot of jargon in there, but we can put this into language that we've reviewed in this video. So we could say the researchers assumed the recurrence rate was 30% and asked whether the new treatment reduced the recurrence rate by 1/3 or more. down to 20% or less. And they chose to study 313 patients in each group, so that if the true effect was a 1/3 reduction in recurrence rate, they have an 80% chance of detecting that at a significance level of 0.05. So we're just finished with a couple of observations about calculating a sample size in practice. So the sample size calculation is precise, but the guesses and judgment on the parameters that go into the calculation isn't. So often we like to look at various scenarios when estimating a sample size for a study. For example, we may like to do a sample size for a range of different effect sizes. Sometimes we might work in reverse and calculate what power we would have for a given sample size and effect size. For example, in some situations, we may know that we only have resources to study a certain number of people. So in this case, we work out whether studying a sample of a particular size is likely to give us enough information to answer our research question. If the power is likely to be small, then it's better not to waste resources on a likely futile study.